In this video, we will see about what is a DC generator and the principle of operation of a DC generator. What is a generator? This type of generator we might have seen in small shops. It is used to provide power supply during power failure, and it converts mechanical energy into electrical energy so that you can power all the electrical equipments. What is a motor? So motor, we know it needs electrical input. That is, only when there is a power supply our motor will work. So it converts electrical energy to mechanical energy. Motor generator set, that is, a generator will, if you give a mechanical input, it will give you electrical output. A motor will be given an electrical input and it will give you a mechanical output. The same machine, you can make it to work as a generator or a motor depending upon your requirement. You might have seen this type of configuration in most labs where a motor and a generator will be coupled together. So this motor can act as a prime mover for this generator, and this generated EMF can act as an input for the motor. So this type of combination will be used in many applications. Now let us go to the topic DC generator. So DC generator is a machine that converts mechanical energy to electrical energy. It is based on the principle of Faraday's law of electromagnetic induction. What is that law? So whenever a flux is cut by a conductor, an EMF will be induced in the circuit. So this is the Faraday's law. Now we will see what you mean by Faraday's law of electromagnetic induction. For that you need a magnetic field and a conductor capable of carrying current. This magnetic field can be produced by a magnet, and for a conductor you can take a coil which will be able to carry the current. So here you have to note down three important things. Before that you should note that this coil is stationary, only magnetic field is moving. Okay, coil is stationary, magnetic field is moving. So here you note down, now when the magnet is moved towards the coil, your deflection is positive, and when it moves in the opposite direction, you see here deflection is negative, and when it is not moving, deflection will be 0. So only when there is a rate of change of flux, an EMF is induced or the current is flowing in the circuit if the circuit is closed. Okay. So there should be some movement so that there will be rate of change of flux. So in that case EMF is induced. So if you go in one direction, it will be positive. If you go in opposite direction, it will be negative. And when there is no motion, or it will be 0. That is, when there is no rate of change of flux, it will be 0. Deflection will not be there. No EMF is induced or no current will be there. So here in any machine you have two things, a magnetic field and a conductor will be there, out of which any one will be stationary, the other one will be rotating or moving. So the if the magnetic field is stationary, we call it as a stator, or the conductor can be stationary. Anything can be stationary and the other one can be moving. So the part which remains stationary is called a stator, and the part which is moving or rotating is called rotor. Now we will see about the principle of operation of a DC generator. So already we have seen that it is based on the principle of Faraday's law of electromagnetic induction, and the stationary part here is magnetic field. Okay, so here the magnetic field which is produced by the magnet is kept stationary and only the coil is moving. Okay, so the stationary or stator is magnetic field here and rotor is the conductor. Okay, now the magnetic field is produced by the magnets. So the direction of the magnetic flux is here, and this one rectangle one is the coil, and it will be connected to the commutator. Again you have brushes at two ends. So if you measure across this one, you will get the generated EMF. So this is the axis of rotation of the conductor, that is you are rotating the conductor in the magnetic field. So we have seen that whenever there is a rate of change of flux, as the coil is rotating, it will cut the magnetic flux. So there is a rate of change of flux, so EMF will be produced. The magnitude of the EMF will depend upon the position of the conductor in the magnetic field, that is whether it is at 0 degree or at some angle. Depending upon that, voltage will be produced. So we will see step by step. So here same diagram, but this specifies it is at 0 degree and this is at 90 degree and this is at 180 degree position of the coil. You can see the position of the coil. You see here blue color is up and gray color is down. Okay, so now you are rotating the coil in this magnetic field. So when you do so, what happens at position 1, the rate of change of flux is 0. Okay, so your magnitude is 0. Now I am changing this position by 90 degree, that is the rotating the coil by 90 degree. So if I rotate like this, that is this blue color comes here. So at that time maximum rate of change of flux will be there, and in that case my magnitude is going to be high or peak value I will get. Again if I rotate it by 90 degree, so from 90 it becomes 180 degree, or this blue color conductor which was at the top here, it comes down. So what you should get? Again 0. So it is 0. Next again you tilt it by 90 degree, you rotate this by 90 degree. So it comes to 270 degree of rotation. At that you will get negative flux, because earlier, now it is under north pole, earlier it was under south pole. Okay, so under south pole it is giving positive peak value, means under north pole it will give negative peak value. So again at 360 the rate of change of flux is 0, so EMF is 0. So this is how EMF will be generated in the DC generator. So actual generated EMF will be AC. Because of this commutator you will get a DC output. So the direction of the induced EMF can be found from Fleming's right hand rule. So what is this Fleming's right hand rule? You stretch the thumb, index finger and the middle finger of your right hand at 90 degrees, that is perpendicular to each other. So if you do so, the thumb will give you the direction of the motion of the conductor, and if forefinger represents the direction of the magnetic field, then your middle finger will give you the direction of the current. So from this you can find the direction of the induced EMF. Now let us see the construction of DC generator. So we know you need a magnetic field as well as a conductor for carrying the current. Two things we need. So first let us see about the magnetic field. So this blue color one are called field poles. That is, if you pass a current through the field poles, it will get magnetized to south polarity or north polarity depending upon how you wind the wire or how you pass the current through it. So in this case, you see here the field, this is the field winding which is wound over this pole. So here it will be going from top and then it is coming like this. So in case of this north one, you see it will be wound in opposite direction. Again in south, in same direction as this south, and for north in opposite direction. So depending upon how you wind the wind over the poles, it will attain north or south polarity. So alternatively, you should have a north and south pole. And again you have the armature, which is the green color one is the armature, and you have lot of slots here. In slots, the black color dots are called armature conductors. So that is the coil. So it are inserted in the slots, and this commutator helps to change the bidirectional current into unidirectional current, because we have seen that we are getting an alternative EMF that can be made as a unidirectional EMF by this commutator. So this outer ring is called the yoke, or it acts as a protective cover for the whole machine. So this is the protective cover, yoke, and this windings are called the field windings, and the center part which is movable is the armature winding. And you can see here the field winding is stationary, only the center part is rotating. So that is the armature winding, and it will be connected to the shaft. And one more thing you have to note down here is that these poles will be of horseshoe shape. So this is done so that there will be uniform distribution in the air gap. Uniform distribution of flux in this air gap. So now let us see the parts of a DC generator. So field system, which consists of field poles and field winding, and armature has armature core and armature conductors, and then you have commutator and brushes. The final one is the yoke, which is the outer cover or protective cover. So let us see one by one. First one is the field system. So the function is to produce a uniform magnetic field, and it consists of field poles and field winding. And in the field winding, we will pass a DC current, and they get magnetized to north and south polarity. So depending upon in which direction you wind the windings, it will attain north and south polarity. So the field poles, they are actually laminations of magnetic material, and this magnetic material should have very high relative permeability but very low hysteresis losses should be there. And this pole face will be of horseshoe shape, so that the flux distribution will be uniform in this air gap. And if you take armature, it consists of armature core and armature conductors. So this is armature core, and this black color dots are armature conductors. This armature core, it is actually a slotted drum. So you have lot of slots will be there. So and they are laminated to reduce the eddy current loss. And this armature conductors are placed in the slots, and all the conductors will be connected in series to form the armature winding. So depending upon the manner in which we connect the conductors, there are two types of armature winding. One is called lap winding and the other one is called wave winding. So we have seen that this is a single conductor. Okay, this part is a single conductor and the other one will make a coil, or two conductors can make a single coil, and this is the commutator segment. So one end of the coil will be connected to one segment, the other end of the coil will be connected to other segment. Now we will see what is lap winding and wave winding. So in lap winding, you see here, one end of the coil is connected here, the other one will be connected to the other segment, and in this case the number of parallel paths will be equal to number of poles in the machine. So we have considered a 4-pole machine, that is 2 north pole and 2 south pole are there. So it is a 4-pole machine. So in such cases the number of 4 parallel path is 4. So this type of lap winding will be preferred for low voltage and high current machines. That is, voltage will be low but current it has to carry large current. In such cases you can go for lap winding. Wave winding, you see here, one end of the coil is connected in one segment, whereas the other end of the coil will be connected somewhere in the commutator segment. So here only 2 parallel paths will be there. So in such cases it is used for high voltage and low current machine. And what is a commutator? So this is the coil will be here, the ends of the coil are connected to the commutator segment and brushes will be pressed against this commutator. So commutator is actually acts as a rectifier which converts the alternating voltage into direct voltage in the external field. So alternating EMF produced will be converted into a unidirectional one. How do this commutator change a bidirectional voltage into unidirectional voltage? You see here the conductor AB is at the top and it is connected to the segment A of the commutator and CD is connected to the segment B. When this coil rotates, and you can see here the current flows from through the load in this direction. So the arrow is specified here. So this is the current direction in the external circuit. So when this coil rotates, so that is CD has come to the top and AB is here. Now you check, this AB is connected to again to segment A. So when the coil rotates, this segment will also rotate. So the current through the external circuit, if you see, it will be always in the same direction. So this is how a bidirectional voltage is converted into unidirectional voltage. When the coil rotates, this commutator segment will also change its position to make this bidirectional voltage to unidirectional voltage. Always the current through the external circuit will be in the same direction. So in between the two commutator segments, there will be a mica sheet to insulate one from the other. And you can see here the coils are connected to the different commutator segments. Next we have brushes. So they are used to collect the current from the commutator and give it to the external load. So you can see here brushes, they are connected to the external load, or the brushes helps to receive the current from the conductor or commutator and give it to the load. So they are made up of carbon or graphite, and in case of multiple pole machine you may have multiple brushes. So the points to remember about DC generator are: it is a rotating machine that can convert mechanical energy into electrical energy, and it is based on Faraday's law of electromagnetic induction. What is that law? Whenever a flux is cut by a conductor, an EMF will be induced. The direction of the induced EMF is given by Fleming's right hand rule. If you take a right hand and keep the thumb, forefinger and the middle finger at 90 degrees to each other, and if the thumb points in the direction of the motion of the conductor, forefinger in the direction of the field, then the middle finger will give you the direction of the induced EMF. If you like the material, do subscribe to Read Electric Vehicle channel. Thank you.